Hello, we're Group 7 and we'll be talking about the design and simulation of a centrifugal pump. Here is your index. Centrifugal pumps are turbo machines used mainly in the transport of liquids, which transform mechanical energy into hydraulic energy, transferring energy to the liquid, which facilitates its mobility from areas of lower to higher pressure. These machines are widely used in a great variety of industries, therefore, they have a great number of variables which are used to satisfy the specific needs of each process. The objective of this project was to design a pump that complies with these restrictions and specifications given by the manufacturer. Additionally, an analysis of the pump's performance under different operating conditions and geometry was carried out. For the dimension and geometry, the preliminary design of our pump is based on the BEP of the manufacturer, where we use this data to create the distribution of the blades in the impeller, the geometry of the volume, and to create the pump itself. Our parameters were a beta 1 of 20 degrees, a beta 2 of 30.4 degrees, 6 blades in total, and a diameter of D2 of 0.308 meters.
Here we are able to see all physical models that we use. However, we are going to mention just the principal ones, which are steady flow, that this assumption will reduce the convergence time, constant density, that the fluids were not compressible, segregated flow, this allow to decrease of the computational time necessary for the simulation. In addition, it resolves the equation for velocity and pressure for each fluid. Boundary conditions. The operation temperature was 20 degrees Celsius and the operation pressure was 1100-325 Pascal. And finally, key epsilon model. Key epsilon model was chosen because this model contemplates the dissipation rate and kinetic energy due to the turbulence regimen. Now we are going to talk about initial and boundary conditions. The simulation was established using two different fluids, water and mineral oil, both at the same temperature of operation but varying their density and viscosity. Because the flow rates were given in cubic meters per hour, we used the density of each fluid to determine the mass flow rate, which was our boundary condition for the inlet in each simulation.
For the CAD design, through the use of Inventor and using the dimensions and geometry, we created a 3D model of our pump that met the requirements of the manufacturer, where we then exported the files to Star CCM to work on the different simulations. When creating the mesh, we use polyedral mesh, Prim's layer mesh, surface remeasure as the measures. Surface remeasure improves the overall quality of an existing surface and optimizes it for the volume mesh models. Polyedral measure model is more accurate than tetrahedral mesh because it is numerically more stable and less diffusive. Thin measure generates a prismatic type of volume mesh for thin volumes within parts or regions. Prim layer measure considers the profiles formed in the liquid-solid interface, allowing better modeling of the fluid.
With the mesh-independent test, the MSE obtained in this case was of 1.83%. This test allows us to optimize our simulations and view which type of mesh provides us with the most desirable results. As seen in the graph, when an increase in the number of cells, or MSE, is lower and provides a closer result to the manufacturer. However, an important factor that impacts is the computational time. This increases as well with the number of cells, so taking all of these parameters into consideration allows to determine which mesh is more optimal. In this case, considering that the MSE difference between our BP mesh and fine mesh is around only 0.8% difference with a faster 15,400 seconds of computational time, it benefits more to use this type of mesh, which guarantees in a faster time to get accurate results. The following scenes show the results for the velocity, cavitation, and worldwide plus for a simulation. Here we have the results for the BP manufacturer. Here we have the results for the shut-off simulation. Here we have the results for the intermediate simulation. Here we have the results for the free delivery simulation. And here we have the velocity for a BEP group's design.
The phenomenon of cavitation involves the formation and presence of bubbles due to the phase change of the substance from its liquid state to the vapor state. It is expected to have a loss of pressure in the water cutoff because of the volume's expansion in the diffuser. Furthermore, it is expected to have low pressure in the rotating zone due to the increase in the velocity caused by the impeller. It is noticeable that the cavitation phenomenon occurs between the suction flange and the impeller side. This phenomenon occurs because of the pressures obtained in these areas are less than the pressures of saturation of the fluids, which are 2,337 pascals for water and 13.33 pascals for oil. The value of the wall J plus is a dimensionless measurement given by the Reynolds number. This parameter indicates whether the universal law of the wall can accurately predict the wall-bounded turbulent flows. It also determines the relative importance of viscous and turbulent processes, meaning that in our simulation its value will vary depending on the physical properties of the fluid, since the mesh was kept constant for both water and mineral oil. This can be seen by the significant difference in the value of all J plus between water and mineral oil for all simulations.
Here we can see the videos of the streamlines animations of both BIPs, the manufacturers and the group's design. In the animation videos, we can see the behavior of the flow, but showing the velocity vectors. The CFD versus manufacturer. Both efficiency and head reports for the simulation are compared with the values of the manufacturer, in which seen by results obtained, the CFD results are very similar to the manufacturer. However, they are still not exact, which can be contributed to different factors, such as the fact that CFD software does not consider mechanical or volumetric losses when simulating, which are factors that can greatly impact the pump. The RMS for head calculated is 164% and for efficiency 0.74%. The operation curves shows the behavior and the performance of our pump design. The most important variables to consider are the flow rate, the total head, the efficiency, the brake power, and the hydraulic power. We obtained two graphics of the operation curve, one that contains all of the previous variables in the y-axis and in the x-axis only the flow rate. All of this with the conditions of the water. The second graphic shows the operation curve exactly as the first one, but with the conditions of the mineral oil. The results shows how the total head decreases with an increase of the flow rate, as well as the fact that for the mineral oil, which has a bigger viscosity, the total head is lower than water, due to the fact of frictional losses present by the viscosity in the fluid simulated. Also, the efficiency calculated is higher for water, which stays true to the pattern present in the total head. If we analyze just through our results, what would be our BP flow rate given our efficiency? It would be 48.47 kilograms per second, which is lower than the BEP for the manufacturer and the group's own design. In terms of brake power effectively, we can evidence that it is higher for mineral oil than water due in part to the higher viscosity of the fluid. As mentioned in Valdez 2020, this increase in the brake power for mineral oil is due to increase in viscosity, which in part increases the fractional losses present. The analysis of the hydraulic power can be given due to the fact of variation of the flow rates, in which due to the difference in densities. Our mass flow rate for water is higher than our mineral oil. The BEP mass flow rate for water is 50.46 kilograms per second, while for mineral oil was 43.6. This difference present in the flow rate is what gives a much higher hydraulic power output than mineral oil.
Finally, we have the conclusions. First, the mesh that we obtain in which we get over 1 million cells is not the best, and because of this reason we should improve our design. The principal reason of this is that our wall Y plus is kind of high. Second, the physical conditions of the fluids have an impact on the output of our pumps based in the results obtained from the CFD. The viscosity of the fluid has a high impact in the results of the pump, affecting the total head, efficiency, and brake power obtained. Third, the reasons why cavitation occurs in both water and oil in the BIP can be explained by a bad pressure reference point when running the simulation, because it was not verified that this point was within the fluid. Because of this, it is key to consider the continuity equation alongside Bernoulli laws of fluid to understand this phenomenon. In order to reduce cavitation, it is best to operate the pump in this best flow rate. Finally, for mineral oil, we observe values for Y-wall plus below 5, meaning that the turbulence boundary layer for this substance is in the viscous layer, therefore its behavior is governed by the viscosity effects and laminar regiment. On the other hand, some water simulation shows values within the buffer zone, meaning that the large error calculating the shear stress can be found. For this simulation, we would need other type of correlations in order to have a better understanding of the substance near the wall area. Reference and thank you.